3I Atlas has reached its closest point to Jupiter, passing at approximately 53.6 million kilometers and undergoing a measurable gravitational deflection that has permanently altered its trajectory. Traveling on a hyperbolic path at tens of kilometers per second, the interstellar object was not captured, but its exit vector from the solar system has been recalculated as a direct result of Jupiter's influence. This encounter marks the only significant planetary interaction on its outbound journey, establishing a new course that will carry it past the orbit of Saturn and ultimately beyond Neptune into interstellar space. 3I Atlas has passed near the outer boundary of Jupiter's gravitational dominance, the region known as the Hill sphere, where the planet's pull begins to outweigh that of the Sun. It was not a close encounter in the dramatic sense of tidal disruption or capture. The object was moving far too fast for that, racing through space at tens of kilometers per second on a hyperbolic trajectory that guaranteed its eventual escape. And yet, Jupiter's immense gravity was enough to nudge it. The deflection was small, measured in fractions of a degree, but in the vast geometry of space, even such a tiny shift translates into a fundamentally different exit path from the solar system. This kind of gravitational interaction is not unusual in principle. Jupiter has long been known as the solar system's gatekeeper, capable of redirecting comets, capturing some, ejecting others, and occasionally sending objects plunging inward. But what makes this encounter different is the nature of the object itself. 3I Atlas is not bound to the Sun. It did not originate here. Its trajectory is hyperbolic, not elliptical, meaning it arrived from interstellar space and will return there. It is only the third known visitor of its kind, following in the footsteps of Oumuamua and 2I Borisov. But unlike its predecessors, it has traveled a path that intersects closely with multiple major planets. After its encounter with Jupiter, 3I Atlas is now accelerating outward, moving away at well over 200,000 kilometers per hour. Its trajectory will carry it past the orbit of Saturn in the coming months, though at a much greater distance than its Jupiter approach. By 2028, it is expected to cross the orbital region of Neptune, marking the final stage of its passage through the solar system before it disappears into interstellar darkness, never to return. Since its discovery, 3I Atlas has ignited a wave of attention, speculation, and debate, unlike anything we have seen. The reason lies not just in where it came from or where it is going, but in how it behaved along the way. From early observations, the object began to display characteristics that many described as unusual, if not outright anomalous. Its trajectory alone raised eyebrows. Unlike most comets, which approach the solar system from random inclinations, 3I Atlas followed a retrograde path that aligned unusually closely with the plane of the planets. Statistically, such alignment is rare. More striking still was the timing of its journey. It passed relatively near Mars, then continued inward, threading a path that brought it into proximity with Earth's orbital region before swinging past the Sun and heading outward toward Jupiter. Each of these encounters occurred within distances that, while not dangerously close, seemed finely tuned, close enough to be scientifically valuable, yet distant enough to avoid disruption. Then came the Jupiter encounter itself. The object's closest approach distance appeared to coincide almost perfectly with the boundary of Jupiter's Hill sphere, within a margin of roughly 100,000 kilometers. In cosmic terms, that is an extraordinarily tight alignment. Some observers interpreted this as coincidence. Others saw it as something more deliberate. The behavior of 3I Atlas became even more puzzling when astronomers began studying its jets. Comets typically produce tails that stream away from the Sun, driven by the sublimation of ice as solar radiation heats their surfaces. But 3I Atlas appeared to defy this expectation. It exhibited a prominent anti-tail, a jet that seemed to point toward the Sun rather than away from it. This structure extended hundreds of thousands of kilometers and maintained a remarkably narrow collimated shape, far more focused than the diffuse tails of typical comets. In addition to this anti-tail, the object displayed three smaller jets arranged symmetrically around its body, spaced approximately 120 degrees apart. These jets appeared stable over time, maintaining their orientation despite the object's rotation. Even more curious was a wobble observed in the jet structure, which seemed to shift in a way that corresponded with changes in the object's orientation relative to the Sun. Before perihelion, the jets behaved one way. Afterward, they appeared to flip while still maintaining directional consistency, such coordinated behavior is difficult to reconcile with simple models of uneven surface heating. Motion analysis added another layer to the mystery. Like many comets, 3I Atlas exhibited non-gravitational acceleration, likely driven by outgassing. But in this case, the acceleration was not directed purely away from the Sun. Instead, it included a significant sideways component, altering its path in a way that standard models struggle to fully explain, rather than behaving like a passive object pushed by solar heating. It appeared to be adjusting its motion in a more complex manner. Composition studies of 3I Atlas further intensified scientific interest, revealing a combination of chemical and isotopic properties that set it apart from known cometary bodies. Spectroscopic observations of its comet detected elemental ratios that defied expectations. Nickel, typically a minor component in cometary material relative to iron, was found in greater abundance than iron, a reversal rarely if ever observed in natural comets. This unusual enrichment immediately raised questions about the processes that could have produced such a composition in an interstellar environment. Methanol, a simple organic molecule often present in trace amounts in comets, was detected at concentrations far exceeding predictions based on standard models of icy body formation. Early measurements of water content were equally surprising. Prior to perihelion, water accounted for only about 4% of the observed mass, an exceptionally low figure for an object originating from a distant star system. Following perihelion, however, water emission increased dramatically, producing a sharp spike in abundance. The sudden variability in water production, combined with the persistent high levels of methanol, implied that the object's volatile behavior was not consistent with standard sublimation processes seen in solar system comets. Isotopic analysis added an additional layer of anomaly. The ratio of deuterium to hydrogen in the object's water was significantly higher than that measured in typical solar system comets. Deuterium, a heavier isotope of hydrogen with one neutron, is generally indicative of formation conditions and chemical history. Elevated levels suggest that 3I Atlas originated in an environment very different from that of our Sun, potentially in a low metallicity or chemically distinct star system. Similarly, ratios of carbon isotopes hinted at further deviations from expected interstellar norms, raising additional questions about the object's formation history and the processes that shaped its chemical makeup. Photometric and optical observations reinforced the sense that 3I Atlas was far from ordinary. As it approached the Sun, the object brightened rapidly, exceeding the rate typical of known comets, and simultaneously shifting toward a bluer spectrum. This combination of rapid luminosity increase and color change is unusual. It implies either a different composition of the reflective surface materials or a complex interaction between dust and solar radiation. Polarization measurements of scattered light provided further evidence of unusual material properties. The dust within 3I Atlas's coma interacted with sunlight in ways that differed from the scattering patterns of standard cometary grains, suggesting either an uncommon mineralogy, atypical particle sizes, or an organized structure not commonly found in natural comets. Collectively, these chemical, isotopic, and optical anomalies reinforce the impression that 3I Atlas was an interstellar object of exceptional and highly unusual character, providing a rare opportunity to study material from beyond the solar system. Some observers noted that its arrival direction aligned roughly with the region of the sky associated with the WOW signal, a famous unexplained radio burst detected decades earlier. While the statistical significance of this alignment is debated, it added yet another layer to an already complex picture, taken individually. Many of these features could potentially be explained within the framework of natural processes. Comets are messy, dynamic objects, and interstellar ones may differ significantly from those formed within our own solar system. But taken together, the sheer number of unusual characteristics led some to propose more speculative interpretations. Among the most prominent voices in this discussion is Avi Loeb, who has argued that certain interstellar objects may warrant consideration as technological artifacts rather than purely natural bodies. In more speculative circles, 3I Atlas has been described as a potential alien asteroid ship. The argument is not based on a single observation, but on the accumulation of many. The precise trajectory, the structured jet system, the unexplained components of its motion, and the unusual chemistry are all cited as pieces of a larger puzzle. Some have suggested that the jets could represent a form of propulsion with the symmetric arrangement functioning as a control system. Others have pointed to the high deuterium content as a possible indicator of fusion-based energy processes, or to the methanol abundance as a potential propellant. As it continues its journey outward, the object grows fainter with each passing day. Instruments will track it for as long as possible, extracting every bit of data before it fades beyond detection. By the time it crosses the orbit of Neptune, it will already be little more than a point of light. Receding into the vastness from which it came, what remains is the record of its passage. A brief, complex, and deeply intriguing encounter that has challenged assumptions and sparked imagination. Whether 3I Atlas ultimately proves to be an exotic but natural comet from a distant star system or something more unusual, its visit has already had a lasting impact. It has forced scientists to confront the limits of current models and has reminded the public that the universe still holds surprises.